Pablo on all things graphene.
Okay, thank you very much again. And thank you for being here. So I'm going to take it directly where we left yesterday, but I'm going to remind you of a little bit of what we did yesterday. Okay? So if you remember, I'm talking about transporting graphene, and in particular in graphene hexagonal boron nitride heterostructures. And yesterday, I spent most of the time telling you about what happens when you put graphene on hexagonal boron nitride with a large twist angle, with a large angle between the two crystalline lattices. Okay, then hexagonal boron nitride is a really very high quality substrate for graphene, and then you can really investigate the pristine properties of graphene. And in particular, we look at the quantum spin Hall effect. Okay? Today, what I want to tell you about is what happens when you put graphene on top of graphene. Okay? Which may or may not be on top of hexagonal boron nitride, but again, the hexagonal boron nitride doesn't play any role other than being a high-quality substrate. Now we have graphene on top of graphene, okay? And let's see what we get there. Now, as a reminder of yesterday's lecture, okay? Let's see how can we get quantum spin Hall from quantum Hall edge states. Okay? So this is the Dirac cone of graphene. Okay? If we apply a magnetic field, yeah, that means that electrons in the conduction band will start moving, charged particles, they'll move one way. Electrons in the valence band, they move in the opposite direction, which means that if you are in the quantum Hall regime, if your Fermi level is in the conduction band, your edge states move in, let's say, clockwise. If your Fermi level is in the valence band, your edge states move counterclockwise. Okay? So now, remember that we have not just one copy of this Dirac cone, but we have 4 copies of this Dirac cone. Let me, for now, only think about the 2 copies which have to do with spin up and spin down. Okay? So I'm going to just show you these 2 copies of the Dirac cone. One copy has spin up electrons, the other one has spin down electrons. So if we now apply a Zeeman field, okay, is a Zeeman field, then we split these 2 cones in energy. Okay? So if I keep charge neutrality, my Fermi energy in one of the Dirac cones is in the conduction band, in the other one is in the valence band. So that means that simultaneously I have these opposite spins, which means if I have quantum Hall regime, I'm going to have opposite chiralities coexisting, okay, in my system. So I'm going to have these 2 copies while my Fermi energy is at charge neutrality. I'm going to have something going in this direction, something going in this direction. And since this happens at the same time, what I have is this. I have coexisting quantum Hall edge states in the presence of a Zeeman field in the quantum Hall regime, which have opposite spin polarizations and opposite chiralities. Okay? So this is Zeeman plus quantum Hall gives you quantum spin Hall at charge neutrality. Okay? This is, as I commented yesterday, a symmetry protected topological insulator, okay, which occurs in a magnetic field and also in the presence of electron-electron interactions. And remember that, I told you yesterday, in order to do this, you need to really boost the Zeeman field, so you need fields of the order of 30 plus Tesla. Yep.
I'm sorry if you already mentioned this. Why do the electrons in the conductor band?
Oh, so just think of a semiconductor. The mass of the electron is positive here and negative here. So when you apply a force, the Lorentz force makes one's going one way, the other's going the other way. Yeah. So the same thing happens for electrons in graphene. Now, I showed you yesterday this data. This is the conductance as a function of Fermi energy or density. Okay? And if you have purely perpendicular field, graphene is an insulator at charge neutrality. If you now increase the parallel component of the magnetic field, so you increase the Zeeman field, then you turn it into a conductor with a conductance which is very close to 2 e²/h. And what we're doing is we're doing this. We're going from this antiferromagnetic bulk state to this ferromagnetic bulk state, which has counterpropagating edge states. Yeah? Now, let's go back and think a bit more about this. Okay? So what are the Lego sort of building blocks to realize this quantum spin Hall effect in graphene? Okay? Essentially, what we need are 2 copies of the spin polarized quantum Hall effect. Yeah? That's like the basic thing. So it would actually be great if we could have these, we could split these 2 copies of the spin polarized quantum Hall effect and literally put them on top of each other. Okay? Because this could allow us, rather than having to use the huge in-plane magnetic field, we might be able to just use a perpendicular magnetic field, and in fact, a much smaller magnetic field. So now nature has been very kind with us, because it turns out that filling factors nu equals +1 and -1 exchange interactions in graphene lead to a ferromagnetic spin polarized state. Now I'm not talking about charge neutrality. I'm talking about nu equals 1 and -1. Okay, so that means that for nu equals 1 you get spin up going this way. For nu equals -1 you get spin down going here this way, here this way. Okay? And this is easy to see from the cartoons that I showed you yesterday. If you just have a perpendicular magnetic field, okay, remember, this is the type of splitting that you get, which if you put your Fermi energy here so that you're feeling only one lambda level, you see, it's spin up lambda level. If you go to the valence band, there you go, spin down, okay? And it's counter-propagating with respect to this one. So nu equals +1 and -1 are two components that now we can try to put together and realize this quantum spin Hall effect. So how do we do that? So what we do is, we take monolayer graphene, we put on top monolayer graphene with a twist angle so that these are relatively decoupled electronically. Then we apply an electric field between these two layers so that I position the Fermi energy in one layer in the valence band and the other one in the conduction band. And then I apply a purely perpendicular magnetic field so that I reach nu equals +-1 states in each of these layers. Yeah? Then I realize the situation where I have these counter-propagating spin polarized edge states living in different layers. Yeah? So this is something which has many advantages with respect to the thing that I showed you yesterday. For example, we have a lot of control over the total filling factor, charge density, and the electric field between the two layers in the geometries that I will show in the experiment, where we have a dual-gated geometry. This allows us to do this at magnetic fields of order of a Tesla or a few Tesla, and just purely perpendicular. So we don't need to go to the National High Magnetic Field Lab in Tallahassee to do these experiments. We can do them at home. And it admits also possible fractional generalizations. So now you can think of actually putting a filling factor, let's say 1/3 here and -1/3 here, and realize something which is called the fractional quantum spin Hall effect. Yeah? So this is quite a bit more versatile than the other geometry that I showed you yesterday. Yes?
Why do you have to twist them?
You have to twist them because if you don't twist them, if you have Bernal-Stack bilayer graphene, that has a lambda level energy spectrum which is completely different from graphene and properties which are very different from graphene. So you do have to twist them so that you can keep these nu equals +-1 lambda levels.
Between them,
yes. As we'll see what happens with tunneling, but okay. Bilayer graphene, in addition, if you put an electric field, you open a band gap. Okay, so changes too much. You just want to have two Dirac cones and just shift it. That's what we want, not a quadratic thin, which opens a band gap when you apply an electric field.
I miss, how do you make it asymmetrical? Like when you apply a single electric
You're going to see in a moment, okay, how we do that. So this type of twisted bilayer graphene samples have been studied, for some time now by my group and other groups. Okay, this is the type of geometry that you have. We encapsulate this bilayer graphene in between hexagonal boron nitride substrates so that we have very high quality, high mobility. And then we have a bottom gate and a top gate, so bottom and top metallic electrodes, so that we can apply an electric field, but we can also offset both electrodes so that we vary the total charge density and the total electric field independently. Okay? You will see that in a moment in a plot, how we do that. So let me just show you, these are just some data. What happens if I put now the same voltage to my top and bottom gates? Okay? So I'm just adding charge to the system symmetrically to both layers. This is at a magnetic field of 1 Tesla. I measure the two terminal conductance is 4, 12, 20, 28, 36. That's simply twice graphene's quantum Hall effect. So that's twice 2, 6, 10, 14. Okay, so I get 4, 12, 20, 28. Okay, so as you can see, these two systems now conduct in parallel because I'm biasing them symmetrically. I'm putting, I'm having the same filling factor in each of the two layers. I can bias them slightly asymmetrically and at a little bit of a higher magnetic field. And now I can show you this trace where the conductance goes 4, 3, 2, 1, 0, 1, 2, 3, 4. Okay? Here, for example, in this one state, I have one layer in the insulating state at filling factor 0, the other layer at filling factor 1. In this one state here, I have the other layer at filling factor 1 and the former one at filling factor 0. So here now I have a slight electric field, which allows me to have one layer at charge neutrality and the other one at a filling factor 1, for example. And I can do this in a continuous manner, okay? So let me show you, and by the way, the reason why, here you have 2 6/10, so here you have all the symmetries, spin and valleys still present. I increase a little bit the magnetic field, now I break all the symmetries, okay? Interaction effects, break all the symmetries, okay?
It looks like before most of these transitions, there's a little bit
Yeah,
both graphs actually.
yeah. So this is a very well-known effect. In a two-terminal geometry measurement in graphene, depending on the aspect ratio of your sample, before the plateaus, you can have dips or peaks, actually. You will see in some of the later data I'm going to show you, these are peaks. And this just depends on the geometry and the aspect ratio between the two layers. And this was actually studied by Levitov and Dima Vanin some time ago. Yep.
Is there any reason that only happens for positive?
This, in addition, because these are two-terminal measurements, you can have a p-n junction with the metal contacts, which sometimes leads to an asymmetry, which is more pronounced in one polarity than in the other. Yeah, also one layer has a slightly, depending on the type of electric field. I will comment again on this later on, because one layer is p-type and the other layer is n-type. No matter what you do, you're always going to have a p-n junction with your metal. Yeah. Yep.
Yeah, I guess I just still missing something. If you just take single layer graphene,
Yep.
typically it's not a neutrality point, right? Or
It could be or it could not be.
but
Yes.
then you put a gate on and you
And you shift. You make a parallel plate capacitor so that you charge it and you reduce those
Layer, right?
that charge. Yeah. That you had.
okay, but so when you show this bilayer, that's the same thing. You can bias them in
Yeah.
the same direction.
So if I would only have one metallic electrode and not two, then I would only be able to vary the global charge of the two sheets, but not polarize this, okay? So let me show you actually this map, okay? This is a map of the conductance in the presence of a magnetic field as a function of this back gate voltage and this top gate voltage, okay? So if I apply same polarity voltage to both gates, then I'm adding charge to the same layers at the same time, okay? So this diagonal direction is a direction in which I vary the global charge density that I have in my bilayer graphene system without establishing an electric field between the two layers. If I move along this other diagonal, I'm applying opposite gate voltages to the bottom and the top gate. So I'm keeping overall charge neutrality, but I'm polarizing my layers with an electric field. Okay? Is this clear to everyone? This is important. Otherwise, the rest, you won't understand anything. Okay? So this is the line here at the center for which we have total charge density equals 0, but there is plus charge density in one layer and negative, minus density in the other layer, so that we have an electric field applied between the two layers. A larger electric field, the more we move away from this crossing point. Yep?
If the layers of the graphene are really close to each other, it seems like it's much harder to, like the response to the asymmetry would be much weaker than that.
I mean, for same voltages, of course, the farther away, for the same electric field, the farther away the layers are, the more voltage difference there is between the layers, right? So they're right on top of each other, so we have to apply enough voltage to do that.
Top of each other?
They're right on top of each other, 3 angstroms apart. Yep.
So like to change the total charge density, you just make it really small. Like if you want to polarize them, you have to put a stronger field compared to if you want to change the charge density. Or are the gates also really close?
Well, I'm not sure what. The gates are also very close, yes, a few nanometers apart, okay? So that we try to maximize, the geometric capacitance compared to quantum capacitance and so on. But they're indeed, I'm not sure where your question is going to, but there are all kinds of issues related to field penetration and things like that, which we also have to take into account, yes. And the quantum capacitance in particular of each of the two layers also. The zero of the voltage is literally the zero of my apparatus. I have an apparatus connected to my samples and it has a 0, okay? Now, often, for example, in the data that I showed yesterday, 0 did not correspond to charge neutrality. That means that graphene has some impurities that donate some charge to the graphene, and therefore I have to dial my voltage a little bit to offset those charges which are already present in the graphene. Okay? In this case, for this particular sample, there's a little bit of an offset here and a little bit of an offset here, so that cross is not exactly at 0, 0. So let's look, the most interesting direction to look at is this one, in which I keep global charge neutrality, okay? But I'm polarizing my layers as I move away from that global charge neutrality. So what happens, oh no, sorry, before I say that, let me just guide you a bit more in this map. So as in this map, here we are varying total density or filling factor, global filling factor. Here we're keeping total filling factor 0, we vary the electric field. So here I have -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. If I move in this direction, I have 2, -2. So I have total filling factor 0, but I have in one layer 2, in the other layer -2. Here I have 1, -1, here 0, 0, and the same thing here. Okay, so that's how you should see this map. Now, what happens if we measure the conductance along this diagonal trace? Yeah? So this is what we have. The conductance as a function, it's projected on the top gate voltage axis, but it's measured along this diagonal is like this. Okay, it has these two halves. So this is 0, 0. This is 1, -1, -1, 1. And this is 2, -2, -2, 2. Okay? So let's have a look at this. So first, 0, 0. It's insulating at 0, 0. But that's not very surprising. Remember, now I'm applying only a perpendicular magnetic field. And as I showed you yesterday and today at the beginning, if you just apply a perpendicular magnetic field, graphene at charge neutrality is insulating. So I have two layers at charge neutrality, both are insulating, the whole thing is insulating. So that's not surprising, okay? That we have an insulating state here. Now let's think about the following. Let's look at 2, -2 and at -2, 2. In this situation, I have in one layer 2 H modes conducting, in the other layer 2 H modes conducting. They are connected in parallel. They should give me 40 square over H conductance. And yet, I have an insulating state. Okay? So this is something which was the most surprising to us at the beginning before we thought about it. Okay? So what's going on here? What happens is you have interlayer H tunneling, okay? Which means the following. Filling factor 2 and -2 gives you spin up and spin down going in one direction in one layer, and spin up and spin down going in the other direction in the other layer. Which means there's nothing preventing, since these layers are just 3 angstroms apart, there's nothing preventing this spin up, which is propagating to the right here, tunnel to this layer, because there is a spin up state which is going to the left. And you just have backscattering. There's nothing preventing that from happening, so it happens, and you get an insulating state, okay? That effectively gaps out these edge states. Yes?
Isn't this exactly why you twist it?
But here we have, so in the bulk, they are decoupled, but at the edge, these two things are co-propagating, and they're just 3 angstroms apart. So they do have the possibility of tunneling there. Yep.
What kind of modes do you have when they do conduct?
Sorry?
What kind of modes do you have?
Okay, we're going to get to that now. Okay? So this is why it's insulating in 2, -2, and -2, 2. So what happens here at 1, -1, and -1, 1? Okay? Okay. What do you mean by twisting it more?
So there's 2 -2, like you kept twisting the thing more and more and more.
Okay, it's okay. If okay, very good. So that's a question about geometry. These samples are etched simultaneously so that they share the edges. Of course, if we have two planes like this, the edges will not be co-propagating. There will be only tunneling points at the corners, and we have to study what happens there. But if I have any twist angle, as long as it is a large twist angle, and then I etch the sample so that the edges are parallel, then I will get this.
The edge doesn't care which lattice, how lattice is.
The edge, as long as the lattice are twisted by a large enough angle, doesn't care. Yeah.
This means if I have a smaller first layer and larger second layer, you would get that.
Yes. Yes. I mean, you can immediately think of an enormous amount of games that you can play, right? I can have a sample that shares one edge but not the other, because one sheet is larger than the other. I can put them at an angle. I can share only part of the length, and then part of the length for one and then only for the other. There are all kinds of geometrical games that you can play. We haven't played them, so I don't know what the result is, but you can play all those games, right?
Why did you etch the edges?
When it turns out that when you fabricate these devices, very often there are some irregularities that you're trying to get a ultra flat, very clean area of the graphene. So for that you etch, so that you measure transport only in that, and you also have a rectangular geometry because it's more convenient, for example. So now, these two conducting states are the bilayer quantum spin Hall regime, because for 1 minus 1, what you have is spin up in one layer going this way, spin down in the other layer, go the other way around. Now, this guy, if it wants to tunnel in the other layer and backscatter, it has to flip its spin, and that's something that it doesn't want to do, or at least not naturally. Okay, so it's hard to do, and that means it doesn't happen very often, and that's why you have a highly conducting state. Now, in principle, this state should conduct with conductance 2e⁻h if it was perfectly protected. Okay, so we think the primary reason why it's not 2e⁻h is not actually some intrinsic backscattering, but it's this effect that I mentioned before, that because we have one layer p-type and the other layer n-type, your metal contacts tend to dope the graphene either p-type or n-type, which means one of the two layers always exhibits a p-n junction, which has an enhanced resistance with respect to the metal, and that decreases the value of that conductance. Okay? We have made some non-local measurements, which I don't have time to show, which show us that it's a saturation towards 2e⁻h, at least as good as in the other case when we do these non-local measurements. Yeah? But we don't have, in some sense, this is 1.5 instead of 1.9 like the other case. Now, okay, so this is this regime. Okay. Now, the previous map that I showed you, we can replot it in this way, where now, rather than having backgate and topgate voltage axis, I have displacement electric field and total filling factor. Okay, and this is the exact same type of data. It's actually for a different sample, but the exact same type of data. Okay, now this map, okay, every feature that you see here is here in this sort of theoretical model of the way these things should be. Okay, now, the formula that gives you the measured conductance is this, it's basically given by the total filling factor times e⁻h, except for nu total equals 0. Okay, in this case, you have conductance despite the fact that you have total filling factor equal to 0, okay, which is the quantum spin Hall case. Now, these type of bilayer systems have attracted a lot of attention, especially among theorists. Okay, because you can realize all kinds of interesting things. Okay, for example, the fractional quantum spin Hall effect. If you manage to put fractional filling factors in each of the two layers, you can realize all kinds of non-simply connected geometries if you can if you can design your tunneling between your edge modes in each of these structures. I used to think all of these things were like completely crazy, like these theorists, what are they talking about? Now I just think it's very hard. It's still very hard, but as opposed to impossible, it's a big qualitative difference. In addition, if you put quantum Hall, quantum spin Hall, fractional quantum Hall, and fractional quantum spin Hall together with superconductivity and often together with magnetism, you can realize very exotic excitations, beyond Majorana fermions, all these things like Fibonacci phases and parafermions and things like that. Okay, so there's a lot of motivation for experimentalists also to try to do these things, to try to go towards fractions in these systems, to try to couple to superconductors, also to ferromagnets, and try to put everything together and see what comes out. So let me show you some data on our effort to go towards fractions. Okay? So this is the map that I showed you before. Okay, what would this map look like if we included fractional quantum Hall states? Okay, I'm just going to take there at the center and the simplest fractions. You can see that it becomes very quickly very complicated. Okay, and this is really just tremendous simplification of what it would look like. Nonetheless, despite these complications, we have managed to start measuring some fractional quantum Hall states in these bilayer systems. For example, we took a sample to the magnet lab. Again, now the magnetic field is again 30 Tesla, but just perpendicular. And we managed to put, for example, one layer in charge neutrality, 0, and the other layer we could run it from, through integers and fractions, -2, -5/3, 4/3, 1, 2/3, 1/3. Okay. We can also make some electron hole bilayer fractions. For example, we can put one layer at -2 and then run the other one through different fractional quantum Hall states and integer. Okay, as you can notice, it's kind of interesting. You know, if you have -2 and 2/3, this 2/3 takes away from the -2, so that your total conductance is actually 4/3 E² over h. Okay, so it seems that the fractional edge state removes the corresponding fractional part of the opposite spin polarization in the other layer. Yeah? Now, recently we've been able to fabricate samples of higher quality and be able to do these measurements. So now RXY and RXX measurements at magnetic fields as low as 6 Tesla. So we don't have to go again now to Tallahassee to do these experiments. Now we can measure fractional quantum Hall effect in twisted bilayer graphene at magnets that we all have in our labs. Okay, and this is something that is quite interesting, and we just started, and it's pretty decent fractional quantum Hall data. Okay, and now we are trying to work harder to get even higher quality samples. But this 6 Tesla is already compatible with many superconductors. So in principle, we're entering the regime where we can try to put fractions and superconductors together and perhaps explore some of those physics, exotic physics that you guys have calculated and predicted. So now I'm going to switch now a little bit gears, and I'm going to be telling you about our efforts to put superconductors together with graphene. Okay, not at high magnetic field, just at zero magnetic field, but what kind of developments are there in that area. So let's go to induced superconductivity, and in particular, I'll be telling you a bit about Andreev spectroscopy. Yep. Because so you have one graphene sheet. Now think of the band structure, reciprocal space. You have at a given density, your Fermi surface are disks, right? At the k and k prime points. Now you put another sheet on top, rotate it. Now you have the reciprocal space. If you look on top of it, there are these two Fermi disks which are separated from each other. So, and there could be things connecting you, phonons, etc. But there's no direct overlap of the Fermi surfaces at small enough Fermi energies. If you rotate them and align them towards each other, then these two Fermi surfaces start to overlap. And I hope to be able to tell you something about that at the end if I have time. Okay? So now, it has been known already for many years that if you put two superconductors in contact with a normal conductor, with a normal conductor in between two superconductors, you can still have a supercurrent running through this hybrid object. Okay? It was predicted first by Josephson for a superconductor, tunnel barrier superconductor, but then it was realized that superconductor, normal conductor, superconductor also exhibits the Josephson effect. This Josephson effect, okay, the supercurrent that flows between these two superconductors is not driven by a voltage which is applied to it. Yeah? It's something that occurs in the absence of voltage. It's something which is driven by the phase difference phi between the order parameters of the two superconductors that are attached to your normal conductor. Now, so this was predicted a long time ago, but our modern understanding of the macroscopic origin of the supercurrent and the Josephson effect is that Cooper pair transport occurs via a process called Andreev reflection. So what does this mean? What this means is in the following. You have this normal conductor, okay? And imagine you have an electron here with spin up at a certain energy. It's going to reach this normal metal superconductor interface, but it cannot make it into the superconductor because in the superconductor there's no density of states for isolated, for single electrons, in this energy range, okay, of 2 delta. Okay? This is the density of states, quasi-particle density of states in a superconductor, and here you cannot have just electrons at that energy leaving. So this electron, what it does is it grabs another electron from below the Fermi sea, it forms a Cooper pair, and that absence, okay, the electron that it has grabbed, now the absence of that electron is a Hall state which is retroreflected, and it goes in this direction. When this hole reaches this normal metal superconductor interface, it grabs, one electron from the Cooper pair, fills that Hall state, the other electron goes up here and repeats the cycle. And this is a way of transporting Cooper pairs from one side of the superconductor to the other side of the superconductor. Okay? This process, this electron hole process, is a resonant process, okay, that forms states called Andreev bound states. Okay? And if you want to know in general what is the solution for the energy occurring of the Andreev bound states involved in this process, you have to solve a transcendental equation, which in general It's complicated and it depends on the microscopic properties of this junction. Okay? Now I'm going to show here for the very simplest case of a single channel, a quantum conductor in the ballistic limit, in the short junction limit, and for a single channel, this is what you get. Okay? This transcendental equation, which gives you the Andreev bound states energies, which depend on the phase difference between these two superconductors. Okay? This term here appears in the equation, so the energy depends on the phase phi. So the presence of this normal, of the superconductors attached to this normal conductor, okay, modifies tremendously, this normal conductor modify, the density of states in this middle region is modified tremendously, okay? Here you have your superconductor, here you have the superconductor on the left. Here what you have is the first thing that you see is that these, typical divergences, are actually rounded. And then you have these Andreev bound states, which appear in the ideal case here as delta functions inside the superconducting energy gap, okay? And the energy of these Andreev bound states depends actually on the phase difference across the superconductor, okay? This is the simplest case for a short junction. In general, it's quite a bit more complicated. Okay, one has to solve it, and it's not often the case that you can solve it analytically. Again, in this short Wald-Kalpan junction limit, okay, you have a two Andreev bound states, so a pair of Andreev bound states, and the way this energy, okay, of the Andreev bound state depends on phase is like this. Okay, it's given here. Is delta times square root of 1 minus psi sine square phi halves. Tau here is the transmission through the normal conductor. And this is plotted here for the case where the transmission to the contacts is 1. Okay? But still, there is a finite, not one transmission through the conductor itself. Yeah? This is a case that you probably have seen, plenty of you, okay? The Andreev bound states in a junction, because it appears in all these Majorana business and so often when people are motivating this. You can have way more complicated situations, okay? For example, if your junction length is much larger than your superconducting coherence length, which I think I defined. Did I define it earlier? Yes, I defined it here. Yeah? Your superconducting coherence length in your normal metal. Okay? Then you can have a continuum of Andreev bound states, for example, okay? Which fills with density of states your gap. In general, your supercurrent is given by this, okay? It's the derivative, with respect to phase of the energy of your Andreev bound states. Yeah? So your supercurrent varies depending on the phase difference too. Now, there have been only a handful, literally a handful, I think, less than 5 experiments that have measured from a spectroscopic point of view these Andreev bound states. Yeah? There was several of these experiments have been done at Saclay, in the group of Quantronics group. This was the case for three-dimensional metals and for atomic contacts, so 1D case and 3D case. And more recently, they have in some cases in carbon nanotube and indium arsenide nanowire quantum dots, so the 0-dimensional case, where you can see here, this is a direct visualization of the Andreev, states as a function of phase, for example, here, and this is similar. Yeah? Now, the 2-dimensional case has not been explored much, actually. Okay? Now, graphene is a 2-dimensional tunable weak link. Okay? So you can attach superconductors to graphene. Unlike semiconductor heterostructures where the 2-dimensional electron gas is typically buried in the heterostructure, graphene is right at the surface. So it's relatively easy to make contact to it with superconductors, and you can try to explore these things, okay? You can try to proximitize graphene, and you can change your charge density, your Fermi energy with a gate voltage. So in fact, and already quite a number of years ago, we measured this, okay? We had a piece of graphene here, we had 2 aluminum electrodes attached to it, and we could measure, we could bias with current this Josephson junction, and in some range, we would see a 0 voltage drop, which means you have a supercurrent, okay? Now, in this map, in this color map, I'm plotting the differential resistance of this Josephson junction, okay? This dark means 0 resistance, so superconducting state, and, red means finite resistance. You can see that the supercurrent can be modulated with gate voltage, and it's in fact bipolar. You can make a whole supercurrent or an electron supercurrent. It's finite at the Dirac point. Now, these samples, these were the early days of graphene. These were very disordered by today's standards. Okay?
Can you say the relation of, let's say you take that blue line cut, is that related to that plateau?
Yeah, that, let's say that blue cut is one of these cuts. Let's say it's close to charge neutrality, so it's like the 1 volt cut, okay? You see this a region of 0 voltage drop, which means zero differential resistance, that's that region,
Oh, I see.
and then the resistance increases, At high gate voltage, for example, minus 50 volts, you have a larger supercurrent. That's why this region of supercurrent is larger. Okay?
But you said black is conductive?
No, resistance, differential resistance. So zero differential resistance means supercurrent.
Okay, thank you.
Okay? So nowadays we can prepare these samples in encapsulated in hexagonal boron nitride, which are much cleaner, right? So we can make this type of interferometers. We call this PMP ballistic interferometers, where you have a graphene piece, which is connected to two superconductors, and we have on top of it hexagonal boron nitride, also at the bottom, and you can put a top gate, which modulates locally the voltage, so that you can make one of those Klein tunneling experiments, and make a Fabry-Perot interferometer here within this region. Yeah? So if you measure the resistance of one such devices, one of these interferometers, this is the resistance measured as a function of the top gate, which is here on top, and the bottom gate, which is here at the bottom. Okay? Then you can see this is the Dirac point, the resistance maximum associated with the Dirac point when you bias, one gate voltage. This diagonal is the resistance associated with the Dirac point underneath the top gate, and it's at the diagonal angle because the charge density underneath the top gate is controlled both by the top gate and by the back gate. And this slope gives you the capacitive ratio of these two gates, okay, controlling the charge density in your local region. Okay? And then this is dividing this map, depending on the voltage on your gate electrodes, into these regions. If all your voltages are negative, your entire sheet outside and underneath the top gate is p-type polarity. We call this pp prime p. If all is positive, it's n prime n. If you alternate now the voltages, you can have PNP or NPN type of junctions. Okay? And what you see here, these interference fringes here, okay, which I'm going to show you here a trace. I take a cut here. My resistance has these oscillations in the NPN regime. These are Fabry-Perot oscillations in the cavity formed by this top electrode. Okay? And it occurs because the electrons propagate ballistically and they do like in a Fabry-Perot. Okay? And that's why they oscillate. Okay? Now, this is in the normal state. Okay? I have applied actually a little bit of a magnetic field to kill superconductivity. If I now decrease the magnetic field to 0, I can measure in the differential resistance, I can measure for my N prime N, I just measure the regular supercurrent that I was measuring before. But if I go to this interferometer regime, I can measure oscillations of my supercurrent, which occur, in phase with the oscillations in the normal state resistance, okay? Meaning that I have ballistic supercurrents propagating through these junctions. So this is just to show you that nowadays we have extremely high quality Josephson junctions where supercurrent can be propagated ballistically, okay? So we're really making progress in making contact between superconductors and high quality graphene devices. But this is measuring the supercurrent. This doesn't give you direct access to the Andreev states, for which you need to, when you measure conductance, you don't have access to the energy scales in your problem. In order to have access to the energy scales in your problem, you need to do tunneling spectroscopy, usually. So this is what I want to tell you about now. Yeah? So we're doing the following type of experiments. We have our graphene sheet. We have a tunnel barrier, which is going to be a monolayer, a single atom thick, one monolayer of hexagonal boron nitride. And then we are going to have a tunneling electrode. And this tunneling electrode allows us to access the energy scales, okay? The energy axis, as opposed to transport, which allows you to access the density axis. Okay? In addition to accessing energy, because we still continue to have our gate voltage, we can also access density. So this is going to be a richer set of experiments that I'm going to show you. So what you have is graphene contacted by superconductors. It becomes proximitized. It's opened a band gap, a superconducting gap in the graphene. I'm going to tunnel. The differential conductance now is going to be proportional, as you know, in tunneling to the density of states. Okay? And it's going to depend also on the Fermi energy, which I can control with my backgate electrode. These samples are quite sophisticated, in fabrication in general. Let me show you. This is the basic schematics. What I have is a graphene sheet which is on top of hexagonal boronitride, so that it's of high quality. Then I have a monolayer of HBN. This light blue is a monolayer of HBN. That's my tunnel barrier. And then I have a finger here. We choose a graphite finger. That's going to be my tunneling electrode. And I'm contacting the graphene with this aluminum squid loop so that I can thread a magnetic field and change the phase difference across my graphene, okay? So I have full control over phase density, and I have access to the energy because of this tunneling probe. So let me, and this is what an actual picture looks like of these devices. This is an optical picture, and if you zoom in here, you can see this is an atomic force microscope picture. You have to have good eyes to see that this, this is the graphene. This is a monolayer of HBN on top. You see this tiny step, it's 3 angstrom thick step, and then you have your graphite tunneling electrode. Okay? This is before we put the aluminum squid on the 2 sides. So now, what does this look like? Okay, if we now take this device, sorry, yep. It's so that we can vary the phase difference across your graphene. Of course, to proximitize, it's superconducting, right? So yes, so these 2 electrodes form a Josephson junction with the graphene, and we close the loop so that we can apply, thread it with a magnetic field, and vary the phase difference across the 2 electrodes, okay? When we apply a magnetic field, the phase of this left side and the phase of this right side superconductors are different, okay? And we're going to be able to vary that continuously. So this is the differential conductance measurement as a function of bias. So this is my energy axis now, okay? For a particular gate voltage and at 0 magnetic field, okay? As you can see, you have typical tunneling density of states, for a superconductor, okay? But notice, this is not 0, so we have a soft BCS gap. We have presence of density of states inside, okay, the graphene. But we're tunneling now into the graphene. The graphene is proximatized. It has a gap. This gap is 2 delta. This gap 2 delta is about 340 microelectron volts. It's consistent with aluminum. 2 delta for aluminum is 360 microvolts. So the gap is a bit smaller, as you would expect from something which is proximatized, okay? And it's very much consistent. Now, we can vary the magnetic field to vary the phase. So we can repeat this tunneling spectroscopy as a function of phase difference. Okay? So as we vary, in this case, the magnetic field from about 80 to 260 microtesla, this thing gets modulated. Okay? I'm plotting down this modulation continuously here. Okay? This color plot is showing you on this axis bias voltage or energy, if you want, and this axis magnetic field. Okay? And I'm plotting in the color scale differential conductance. And you see how this is modulated periodically. Okay? The period of this modulation corresponds to about 350 microtesla in magnetic field, which gives us an area of about 6 square microns, which is indeed the area of our squid loop. Yeah? Which means every time I put 1 flux quantum to a squid loop, you go back to where you were. Okay? So this is this periodic modulation. What you're seeing here is very much the same thing that I showed before. Okay? In this energy axis and this flux, okay? There's this modulation of the Andreev bound states in your system. That's the modulation that you're seeing here, okay? Except that there is a difference. In reality, because graphene is a 2-dimensional system, okay, what we have is something a lot more complicated. We have a mixture of short and long length Andreev bound states, okay? These short segments give you a strong modulation with magnetic field. The long segments, which are these things here, have a much weaker modulation and give you a soft gap, density of states inside your BCS gap. Sorry? Of the Andreev bound states. So you have each conducting channel in your graphene creates a pair of Andreev bound states. If you take one channel, okay, and in a it's a channel a la in a Landauer-Buttiker, one mode, okay. So yeah, so it's one mode, which is a wave function, which will be let's say geometrically will be short, just going from one electrode to the next in straight line like this. Okay, that gives you a pair of Andreev bound states. That mode would be in the short junction limit. But as you have a 2D, you have higher and higher momental states. Those correspond to angular trajectories, which have much longer geometrical paths. Those create many Andreev bound states.
So really, it's the angle that you're coming in.
Yes. Yeah. Yes. That is if it was ballistic. In addition, of course, you have disorder, which means your geometrical paths for the formation of some of your modes are effectively longer because the disorder is making them, take a longer route to go from one superconducting electrode to the next. Okay. So now we can do all of this now as a function of density in the graphene. Okay. So remember, we have energy axis, we have phase difference. Now we have also density, Fermi energy in your graphene. Yeah? And this is what happens, okay? This is a map of, again, the differential conductance as a function of magnetic field and energy, bias voltage. And now we start here from the highly p-doped, so deep in the valence band, my Fermi energy. And then I bring it closer and closer to the Dirac point. Now I am around the Dirac point. Now I'm going into the conduction band. Now I'm going deep into the conduction band. Okay? So we can see how the modulation of the Andreev bound state spectrum changes as a function of Fermi energy in the graphene. Okay? So as you can see, this has complicated patterns which vary in modulation. What happens near the Dirac point? Okay, these are 3 data sets very close to the Dirac point. Okay? Here, as you can see, there is a very weak modulation of the Andreev bound states. Okay. What happens here is that even in these very high quality samples, as you get sufficiently close to the Dirac point, you start to see the disorder, which is still residual disorder, which is present. Okay? So you enter a regime where what you have is diffusive transport right at charge neutrality in the graphene through electron hole pockets. These electron hole pockets means that on one hand, you cannot reach the very fewest number of Andreev bound states that you would have if you could be very, very close to charge neutrality, because effectively your density is actually higher. So you have more Andreev bound states that you would like to have because of disorder. And because you have a reduced mean-free path, because there you start to see all the disorder when your Fermi energy becomes very low. That means these paths are much longer, and you have long diffusive junctions for which you expect very weak modulation. Okay? We can go to the opposite regime. We can go to very high density. Okay? And at high density, you have very high modulation of your Andreev bound state spectrum. In fact, in these traces, you can see that here at pi, you have an almost flat, just a little bit of a dip, almost flat, so no gap there. Okay, this is the situation that occurs when you are near pi and you have very high transmission through your system. If your transmission is close to 1, this thing closes to 0, and you have no gap, literally. Okay. Oh, I'm sorry. Yes, color are different magnetic fields. Okay, so the deepest is when you are here going through the middle. This blue one where there's almost no deep inside is when you go through here or here, which corresponds to pi phase difference. Okay, so you can see that we can look at this. So this tells you that in these 2 different density regimes, at very high density or at very low density, you're going through either effectively a ballistic junction, or through a diffusive long junction. Okay, and this has different limits for the Andreev bound state spectrum. What we were very surprised to see also is that in some ranges in density, okay, what we saw is that there were oscillations of the, let's say, tunneling density of states well outside the gap. Okay. This is shown here. Now, the contrast with this projector is a bit hard to show, so I anticipated that would probably be the case. So I'm removing a background here. Okay, I'm removing a background here. I'm removing a background here, so that you can see that this is delta. Okay, and this is minus delta. So 2 delta is this, and you have modulation of your density of states well outside the gap. Okay? So we were a bit surprised by that at the beginning, but then we realized that this had actually been theoretically predicted. These are not Andreev bound states. These are called Andreev scattering states, which have never been seen before to the best of our knowledge. But what happens is that you can actually have still Cooper pair transport if this process happens above delta. Okay? The probability for Andreev reflection is, in the ideal case, okay, for perfect transmission, is 1 below delta. But it decreases slowly. It doesn't decrease abruptly to 0 as you go higher in energy. Okay, it decreases slowly, and this can lead to Andreev scattering states, which we believe are responsible for the modulation at values, of a few times delta in our junctions. Okay? So with this, I've finished the superconducting part. This was just to give you a little bit of a flavor of the status of our experiments with superconductors attached to graphene. And yeah, you have a question? Yes, so what this means, you remember the diagram that I showed you before where we had, let me see if I can quickly do this and go, where did I? Here, okay, it's turning out to be a long way, yeah, here, yeah? This electron, you have a normal conductor, you have an electron there at some energy, E. That energy is below the gap, yeah? This electron reaches the normal metal superconductor interface. Cannot jump into the normal metal, it cannot jump into the superconductor because there are no available states for single electrons in the superconductor. To be in the superconductor, you have to be in a Cooper pair at the Fermi energy, or as a quasi-particle at energies above delta. So this electron cannot make it as a single electron here. What it does is, it grabs another electron from below the Fermi sea. Two electrons can jump now as a Cooper pair, but because it has grabbed one electron from here, it leaves a hole, the absence of an electron here. It leaves a hole which is retroreflected. This hole comes here, and now there is a Cooper pair waiting here to one of the electrons of the Cooper pairs fills this hole, the other electron does this thing and repeats. Yeah?
In this Andreev scattering process, there are states.
Exactly. So if we now go to energies above delta, what happens is the following. What happens is the following. This electron is in the normal metal now. Now it has to decide, do I go as a quasi-particle here, or do I grab another electron from here, go as a Cooper pair, and do this thing? And there's a competition between those two processes. The higher the energy, the more likely it's just going to go as a quasi-particle. But the probability for Andreev reflection, it doesn't shut down to zero instantaneously, it goes down gradually.
So it's sort of like a Andreev fabric below.
Well, in both cases, below or above the gap is, you're talking about, because now it's not a bound state, it's a scattering state. Yes. You can see this as, you can indeed see this as a, rather than a Cooper pair and then go in this thing, in both cases. Yeah, here, exactly. Here is just, yeah, exactly. Here is just once and leaving a hole. Yes, indeed. Okay, so now, yep. Yes, of course. That's, as you may have guessed, that's one of the next experiments. I'm showing data which are, unpublished and in preparation, very recent. But one of the first things that we want to do is proximatize twisted bilayer graphene. Yes, indeed.
So what is the reason such a scattering state never be observed?
One of the main reasons is probably that people didn't look for them. Here, graphene is such a more versatile system. We have energy, density, magnetic field. We have so many parameters to play. What people have done in the past, okay, in hindsight, after we saw this thing, we started to talk to some of the experts, especially at Saclay, where they have done a billion experiments related to these things. And people would have, typically they would have just a single trace. They couldn't vary the density, or they couldn't vary the phase difference, or they couldn't vary this other thing. And they saw sometimes some bumps here, but in a single trace, when you see a bump, it's like, it could be this, could be that, who knows? It could be a different type of Fabry-Perot effect, The key thing is that we see that there is something like a Fabry-Perot effect, but now it gets modulated with the phase difference according to the way it should be. That's what convinces you that it has to do with Andreev physics and not a geometrical Fabry-Perot, which has to do with something else. Okay? So it was the combination of having all the knobs available to identify it, I think. It could have been observed earlier. Yeah.
When your lumen is normal, you're seeing if this Fabry-Perot the oscillation. You go to the that you're affecting your conducting channel. It's not just that you're modulating these particles.
For which case are you talking about? But for what type of experiment? For this type of experiment? Because if you go in the normal state, you can also have a fabripero going through your junction, but you apply magnetic field and nothing happens, because there's no modulation of the phase difference because you're in the normal state, right? You know what I mean? So that fabripero is associated with the length energy scale, etc., in your junction, and it has to do with the Fermi. But it's in the superconducting state when you can see that there's a modulation associated with the phase difference across superconductor. Okay. Now, so let me tell you now, switch gears and tell you a little bit in the last half an hour about this physics of the long Moiré wavelength patterns. Okay. So remember, we can play this game both with graphene on top of hexagonal boron nitride or graphene on top of graphene. Yeah, I'm gonna get started with this, and if there's time, I'll tell you something about this. Anyway, I only have a few slides with some recent data on this. So this graphene on hexagonal boron nitride with a small twist angle, forms this Moiré wavelength, and the wavelength depends on the twist angle, as I showed you earlier. Okay, these are direct STM scanning tunneling microscopy measurements of the Moiré pattern. Okay, this is not the graphene lattice. This scale bar is 1 nanometer here. The graphene lattice is much smaller. It's 1 angstrom, right? The lattice constant, and the different size of this is all 1 nanometer in all cases. The different size of these hexagons is just because you're looking at Moiré patterns of different periodicity. Okay, so in this is scanning tunneling microscopy. Yeah, tunneling. Okay, so associated, what we discovered with my collaborator Brian Leroy is that there is the moment you have graphene on hexagonal boron nitride, there's a reconstruction of the electronic spectrum of graphene. Yeah? A new set of Dirac points appears at a energy, and that energy, which we call it the miniband energy, the superlattice miniband energy, goes as 1 over the Moiré wavelength. Okay? That means that you have these extra Dirac points. In a tunneling density of states measurements, a Dirac point, as you know, has a linear energy dependence, so it appears as a dip in your density of states. Okay? So what we would see in these samples is a dip at the main Dirac point, and then at a high energy, usually graphene, you would just go up, but in this type of sample, it would go again and have a dip there. That's how we would know at what energy your superlattice Dirac points were. And we could characterize this energy as a function of wavelength. Okay? As you can see, the energies that are accessible to electronic transport usually, the Fermi energies accessible to electronic transport, are typically about this. So you have to have very large Moiré wavelengths or very small twist angles to see this in a transport experiment. In STM, because we can apply high voltages to our bit tip, we can measure this even for relatively long, smaller Moiré wavelengths. Okay, but in transport, you don't see this unless you have very small twist angle. So we saw, that there was this effect at high energies, this reconstruction of the electronic spectrum and the appearance of new Dirac points, and we asked ourselves, okay, is that the only effect that is present, or is there some effect also here at low energies, at where the original Dirac point is? Okay? So is there something happening there? So we did this type of measurements, 2-terminal electronic transport measurements, and also these quantum capacitance measurements that I already mentioned yesterday. Okay? And these are the type of samples that we have, okay? This type of rectangular devices. The purple thing is graphene, the yellow thing are electrodes, and there is a gate underneath, okay, which controls the density. And these are different samples which have different twist angle between the graphene and the hexagonal boron nitride. So the first thing that you notice when you measure samples with small twist angle is that the resistance versus gate voltage, which, as you know, in graphene, it has just a single peak, okay? Where the peak is where the Dirac point. These samples have 3 peaks, 1, 2, and 3. That's for one angle. The red one has 1, 2, 3, okay? Those side peaks corresponds to, with your gate voltage, you're accessing in energy your superlattice Dirac points. And again, because you have low density states there, you have a high resistance peak, okay? So that was the first thing that we noticed, and that we knew something was strange about these samples, yeah? I mean, not strange. We knew that there was a small twist angle. The thing that I'm doing is, as you see, this resistance axis is in log scale, I have actually just cut this. A usual graphene device, regular, super high quality, normal graphene device with a large twist angle between the graphene and the hexagonal boronite has a resistance at the Dirac point of a few kiloohms. These things have resistance orders of magnitude larger near charge neutrality than what you see in the best graphene, okay? And in the best graphene, if you have pure quality graphene, it conducts even more. So, how high this peak goes in usual graphene tells you about the quality. This thing just was orders of magnitude off, okay? To the point that it was insulating. Okay?
Is that the case for all 4 of those samples?
Yes, there are 4 peaks are on top of each other, yes. Okay? Yeah. But actually, different magnitudes. Okay, I'm plotting now conductance because when, so that you can see that the blue has a larger region of zero conductance than the red, than the purple, than the light blue, okay? And I will tell you the difference between these later, yeah?
But just in regular graphene, how different is the resistance at
The resistance at charge neutrality in graphene, the resistivity, okay? So that we normalize by dimensions. At charge neutrality in graphene, in theoretical, the limit is 40 squared over pi h. Yeah, so of order e squared over h, so of order 20 kiloohms. That's the best at charge neutrality. Oh, away from charge neutrality, it decreases the resistance very much because you have charge carriers.
Yeah.
And it can get down to as low as you want.
That depend on like the scattering?
On the quality, yes, exactly, yeah.
So it would be just infinite?
No, it wouldn't be infinitely thin. That thing has a given shape for the ballistic case. Okay. So this thing made us wonder, okay, it seems like we're actually opening a band gap in graphene. Okay. Now, before I continue the story about the band gap, let me tell you a sort of this, accidental nice thing that happened at the same time. It turns out that these Moiré wavelengths for graphene on hexagonal boronitride turn out to be, okay, for this red and these blue curves devices here, 9 and 13 nanometers. Okay? We can calculate that from the density at which these peaks occur. Okay? And this range, about 10 nanometers, is a very good range to have a super lattice unit cell because of the following. Okay? Turns out that it's very similar to the energy scale associated, to the length scale associated with the magnetic length at high fields. Okay? And you can try to investigate a problem which was, theoretically studied many years ago by Walter Hofstadter, okay, which is the problem of what happens when you have electrons in a periodic spatial potential and in the presence of a magnetic field. Okay? So as you know, the 2 independent problems are very easy to solve. If you have electrons in a periodic potential, that's Bloch's theorem, easy. If you have free electrons in a magnetic field, that's Landau levels, easy. Well, it turns out that if you have electrons in a periodic potential and in a magnetic field, it's very hard to solve. In fact, it took 40 years to solve this thing, until 1976. And that is because your energy spectrum is a fractal. It's in fact the first fractal, I think, that appeared in physics, okay? This calculation. So you can imagine that to calculate this without computers, okay, it's actually pretty hard to do. Okay? So now, you may be wondering, what are you talking about? We have regular materials and we apply magnetic fields and we measure Landau levels, right? Well, it turns out that this fractal, this complexity is only apparent when you have the flux which is piercing your unit cell is of the order of 1, okay? There you have all this complexity appearing. For a regular material where the lattice constant is an angstrom, that requires magnetic fields of order 10,000 Tesla, 100,000 Tesla. So you have to go to a neutron star and do your experiment there, to see it, okay? People have been for quite a while, trying to reach this from the other extreme. Rather than having, 100,000 Tesla, which you can't get, let's try to make a periodic structure with a periodicity as small as we can. And we can, you can try lithographically to define in a 2-deck, for example, a periodic structure with a, but it's very hard to get down to sufficiently small length scales. And if your length scales are not very small, your energy axis, the structure in the energy axis is very small and gets, diffused by disorder, by finite temperature, etc. It turns out that the perfect length scale for the available magnetic fields laboratories on Earth and available temperatures is 10 nanometers, graphene on HBN. So we were very happy to be able to do this. There was, as I said earlier, some earlier work on semiconductor heterostructures, but I don't think it was, as detailed. But if you measure now the conductance of these devices as a function of magnetic field and density, okay, here is what regular graphene could be. You just have a fan diagram. For graphene on HBN with the small twist angle, you have this intersection of fan diagrams, okay? And this actually is a reflection of the Hofstadter butterfly spectrum, the values at which this intersection of lines appears. So I'll show you in a moment. And now this was simultaneously, seen, if there's anything in graphene world, there's actually competition, So these 3 papers were published back to back at the same week, in Nature and Science by 3 independent groups, okay? We all observed this thing.
So I missed, what is varying from panel to panel?
Oh, sample, 3 different samples, okay? In this sample, you see
the angle,
pristine
the
graphene.
angle.
Yes, varies the angle,
Okay, so
okay?
period disappear.
Yeah, Moiré wavelength, unit cell, okay? So now, here I'm showing small magnetic fields, relatively small magnetic field. Let me show you the complete picture. This is what we could do in the lab, okay? We could measure up to 13 Tesla in our lab. And we took the samples to Tallahassee to measure up to, 40 Tesla. And what we see is this. Oh, sorry. First, let me guide you through this thing. These fan diagrams have these lines, okay? These lines intersect at multiples of flux quantum threading your superlattice over an integer. So 1/5, 1/4, 1/3, 1/2. In order to reach 1, which is really being fully into the Hofstadter regime, you have to go to very high magnetic fields, only available at the National High Magnetic Field Lab. Okay? But you can do that. Okay? You could measure up to 45 Tesla, and you can see this feature, which tells you I'm going through 1 flux quantum per superlattice unit cell. And what happens there? Okay? Let me show you. Let's zoom in this region. We're going to be within the n equals 0 Landau level, and we're going to see what happens. Okay? So I'm zooming in there. We're fully into the n equals 0 Landau level. And what you see, theoretically, is this. Below 1 flux quantum per superlattice unit cell, so let me do this. Let me shadow higher. What you have, if you measure quantum Hall effect, is roughly, the Hofstadter spectrum is modifying your band structure and your quantum Hall physics, but roughly what you see is what you expect for graphene in a perpendicular magnetic field, 2, 1, 0, 1, 2. Okay? Here I mentioned these peaks have to do again with this geometry that I mentioned before. But essentially you see 2, 1, 0, 1, 2, 2, 1, 0, 1, 2, okay, that we've seen a number of times now. If you go above 1 flux quantum per superlattice unit cell, you have this. You have this non-monotonic sequence of quantum Hall states, 2, 1, 2, 1, 0, 1, 0, 1, 0, 1, 2, 1, 2. And indeed, in the data, you have this, it's 2, 1, 0, 1, 0, 1, 0, 1, 2, 1, 2, like that, okay? And you're having integer quantum Hall effect and non-integer filling factors, and fractional filling factors. And that's something that occurs because you are in this Hofstadter regime with more than 1 flux quantum per superlattice unit cell, okay? So this was a demonstration that this thing is going on, and it was reproduced at the other groups too.
So when you have graphene on graphene, so the coupling can be made weak by twisting the two.
Yes?
In this case, the twist. So
This case is monolayer on graphene on HBN, not twisted by layer.
coupling first. There is coupling.
Yeah. There is coupling between the graphene and the HBN. That's why you have this reconstruction of the electronic spectrum, okay? But you were asking about graphene on top of graphene, and there's different type of devices which I haven't shown
No,
for the small twist angle.
The degree of coupling depends on the or nitride versus graphene.
Well, it's a completely different thing. In the case of graphene on HBN, you're coupling an insulator to graphene. In the case of graphene, you're coupling, the 2 conductors, graphene to graphene. So the couplings are different, and the consequences are different. Yeah? Yep.
If you perform with the stuff that you showed at the beginning, twisted by the graphene, perform the same stuff with graphene from nitride view.
If you have twisted by layer graphene on boron nitride, or boron nitride, and then I put on top twisted by layer graphene, right? Is that what you mean?
Replace one of the graphene layers. Instead of bilayer graphene, you just use layer.
Well, that's what I'm doing here. It's graphene on boron nitride, right? So that's what I'm doing here, okay? Or what I did yesterday, depending on which twist angle you're interested in. This is small twist angle graphene on boron nitride, okay? Whether it's a monolayer or multi-layer, it's not so important for the boron nitride. Now, I want to go back to the issue of charge neutrality and the insulating state. This black means insulating, and as you can see, it's insulating all through a magnetic field. At high magnetic fields, because of this many-body antiferromagnetic state, which leads to insulating state, but it goes all the way insulating to zero magnetic field. Yeah? So let me show you our capacitance measurements. Remember, I told you yesterday that if you have a parallel plate capacitor, where one of the plates is an exotic object like graphene, which has an energy-dependent density of states, there's a contribution of the capacitance of this object. In addition to the geometric capacitance, there's a contribution which is due to the density of states, and it's called quantum capacitance. Okay? So this is, if you have regular graphene, super high quality graphene, but regular graphene, at very small magnetic fields, so that these many body states have not appeared yet, this is the quantum capacitance that you measure. Okay? Here at zero magnetic field, your density of states is low. But as you increase the magnetic field, the zero lambda level appears. It's a peak in the density of states. For the zero lambda level, that's this bright thing. This is the appearance of the zero energy lambda level in graphene, measured directly by measuring quantum capacitance. This is for graphene with a large twist angle with respect to the Bn. If we have a small twist angle, this is what you get. Okay? You can see a dip at zero, but the zero energy lambda level never forms. You get straight a split peak. Okay? So what is this? Someone asked me yesterday. So by the way, this tells you already that the fourfold symmetry is reduced to twofold. Okay? And it's a strong indication that you have broken sublattice symmetry. Someone asked me yesterday, how different is massive Dirac the same as Schrodinger? Here you see that it's not. Okay? This is massless Dirac. You have a zero energy lambda level, and then the root B dependence for the n equals 1, 2, 3, etc. This is massive Dirac. Your n equals 0 lambda level is split by the mass term. Okay? One of these is associated with one of the k values, this one with the other, with the k prime value. Okay? And the rest of the spectrum is barely modified. Okay? Massive gives you straight lines, okay? Which disperse, including the n equals 0. Massive Schrodinger. Massive Dirac gives you non-dispersive zero energy, okay, but split by the mass term, and then you have the rest going as root B, okay? And this is what we see precisely here in these two terms, okay? So we need, in order to explain our data, both the insulating state and the quantum capacitance measurements in a magnetic field, we need to add a mass term to our Dirac equation, okay? That thing gives you a band gap, and therefore it gives you an insulating state at charge neutrality. It gives you a split n equals 0 lambda level, which is what we see in our quantum capacitance measurements. Moreover, if you now measure this quantum capacitance at high magnetic field, okay, and this is at small magnetic fields, all of these are your lambda levels, okay? Then we increase the magnetic field, you start to see more structure, okay? And then if we zoom in, this is all within the n equals 0 lambda level, okay? These are the 4 lambda levels in the n equals 0 lambda level, okay? You see these fractional states, 1/3, 2/3, 4/3, and 5/3. It turns out that in previous studies of fractional quantum Hall effect in graphene, people did not see 5/3. And they were initially surprised. They would always see 1/3, 2/3, 4/3, and then 5/3 would be missing. It turns out that theorists believe that 5/3 has to do with the excitations to 5/3 are very cheap because of sublattice symmetry in graphene. Okay, and people thought that the reason why you don't see a gap is because it's very small excitation to get to 5/3. Because now we're breaking sublattice symmetry, now we're making those excitations, now we're distinguishing the two sublattices, we're making those excitations a lot more expensive, and that's why you see a very pronounced 5/3, whereas before it was absent. Okay? So we think this is again consistent with the breaking of sublattice symmetry that we see in these devices. But if you think about it, this is kind of strange, isn't it? Because you have a Moiré wavelength of order 10 nanometers. maybe in one region of graphene, locally, you are indeed doing what the simplest, way of breaking, of breaking sublattice symmetry is, let's say, you put graphene, let's imagine it was commensurate with boron nitride, right? So the A sublattice would be on top of the boron atoms, and the B sublattice would be on top of the nitrogen atoms. That would give different potentials to the A and B sublattices. You could break the symmetry, you would open a band gap, and have all these things that I'm telling you about. But the lattices are not commensurate, and we have a small twist angle, which means that even if in one region here locally, your A atom is on top of boron, and your B atom is on top of nitrogen, you just move a nanometer further, and the situation reverses, okay? So you don't have a uniform breaking of sublattice symmetry, right? Your mass term, in fact, is oscillating in space. Okay? You're having AB sublattice symmetry, let's see, plus minus. A few nanometers later is minus plus, and then a few nanometers later plus minus. So you have a mass term which is oscillating in space, okay? So how does this M star depend on the local sublattice symmetry breaking, okay, which in addition varies with lambda? Okay? Let me tell you what's more. We have different type of devices with different Moiré wavelengths, okay? So when we did thermal activation measurements of this gap, what we saw is that depending on the twist angle, we have different gaps, different energy scales associated with this insulating state, okay? So the first thing that, we saw is, okay, let's go and see what theory says. So theory is calculated in the presence of this averaging, this oscillating mass term, which goes positive, negative, does any residual gap remain, okay? Well, it turns out that residual gap remains in third order perturbation theory. It turns out to be much, much smaller than what we see experimentally, okay? Way smaller, the energy scale, than what we see experimentally. So then, plenty of theory papers appeared, my colleague Leonid Levitov, thinks that this could be due to many body effects, which enhance, you sort of open a small gap in a single particle picture, which then due to electron-neutrino interactions gets enhanced very much, okay? There are other, possible explanations, many theory papers. I'm sorry, I didn't include, a very comprehensive list here. Another thing that has been discovered is that when you have the graphene with very small twist angle with respect to the HBN, the graphene can expand itself a little bit to accommodate to the HBN lattice. It does that locally, accumulates strain here, which then releases it in a hexagonal region, in the Moiré pattern, okay? So this is now, you shouldn't see these two lattices as rigid on top of each other. There can be some degree of strain accommodation. Of course, in this, if you have a mass term which is changing sign, that has to give you edge states, right? Where the mass term changes sign. So you have these edge states, in your superlattice. These edge states could be coupled to each other and give you also a big up down. There are all kinds of things, going on, which I think are quite interesting and that many people are studying. So now, since I see that I have still a couple minutes, let me just show you briefly the data on small twist angle, graphene. Yeah, and with that, I will end hopefully a few minutes early. So I showed you, this is graphene. K1 prime. This is the first layer of graphene. Now let me put another layer of graphene on top with a twist angle. This is the reciprocal space for the other layer. Okay, this is what I was telling one of you before. As I rotate those two layers, the reciprocal spaces get together closer and closer. Okay? So that at a certain energy, I start to overlap, and I can start to hybridize my states. Okay? This is the superlattice Brillouin zone that forms, okay, when you have these two, okay, graphene sheets on top of each other, and of course its size is inversely proportional to the twist angle. So this is what the spectrum of graphene looks like for large rotation angle. This is 7 degrees. Energy versus, gamma k, this is the band structure. Let me show you. Okay, so this is 7 degrees. You see there's a slight change, but bare any change of, Fermi velocity, etc. If you go to 1.79 degrees, this is your spectrum. Okay? This is what the spectrum would be of graphene, those two straight lines. This is the actual spectrum of twisted bilayer graphene, 1.8 degrees rotation. You can see it's completely, reconstructed. It has nothing to do with what it had before, right? You can see if you want those straight lines is what remains of those original straight lines, massive change in the Fermi velocity. Okay? In addition, you have these superlattice structures associated with the Moiré potential, which are gapped. They don't form Dirac points because this is graphene on graphene, not graphene on HBN. In addition, you have, okay, let me zoom in. Those are the gapped regions. In addition, you have Van Hoff singularities that occur here and can lead to various instabilities. So this is a very rich system whose properties change very rapidly with minute rotations. Yeah? If I show you the spectrum for 1.6 degrees instead of 1.8, it's quite different. Okay? So just as a, just to show you, what happens, just some data, let me show you something. I'm going to show you that if you put the best conductor in the world at high density, conducting very well, on top of the best conductor in the world at high density, conducting very well, you get an insulator. Okay? So this is what this can show you. Okay? This is the conductance versus density of one of these small twist angle layer graphene. Here you have the low conductance, this in E square over H units. So you see about 2 E square over H, here near the original Dirac point. Now I put a lot of charge density in my system so that each layer is theoretically conducting very well, and what I get is an insulating state, and here I get an insulating state. Okay? Those correspond to getting to that region and getting to that region. Okay? So I put the best conductor on top of the best conductor, and I get an insulator. That's some of the things that you can get in these systems. If you do Hall measurements, you can of course measure also Hofstadter butterfly type of physics. This I'm just showing you. This is the last slide. This is the fan diagram. These are the fan diagrams that come out of the superlattice, miniband structures. If you measure the Hall coefficient, of course, it changes from electrons to holes, back to electrons, back to holes, and it keeps alternating, right, as you go between all these bands. Okay? You can measure what are the filling factors for which conductance plateaus appears. For the original, at very low energies, it still looks like graphene, like massless Dirac. 4, 12, 20, 28, just twice graphene. But if you go to these bands, it actually looks like massive electrons, because in these bands have mass. They're not massless, okay? Up there, etc., and many more things that we're measuring. So now, at the end, and I'm a few minutes early, I believe, I just want to show you the most important slide, which is that, all of this, I don't do all of this, it's actually my group members that do all of this stuff that I've been telling you yesterday and today. And, I've shown you so many data that pretty much my entire group has been involved, so here you have the names, including some of the past group members who are now at faculty positions. And I want to thank you for your attention. Yep. So yeah, I mean, there have been plenty of studies of STM, of graphene on HBN. You cannot measure the sign of the mass term with STM. What you can see, you can, okay, in STM, most STM that have looked into this are STMs that work at several Kelvin in temperature. And in STM, your energy resolution in your bias is not great. So people have seen a flattening of the density of states, which they think it has to do with the gap, but they haven't been able to measure a hard gap by STM spectroscopy. Yeah? But people have seen, of course, the Moiré patterns. I showed them already. They have seen also distortions, accommodations of the strain of the graphene to the HBN lattice. Okay? And they have seen some indications of this gap by STM, but they don't have the precision that we have in transport or the temperatures. Yeah, for graphene on boron nitride, you don't get, in the region where the superlattice Dirac points are there are some bendings there, which I believe some of those may be Van Hoff singularities. I would have to look at the band structure, okay? Yeah. But, and in principle, you should be able to reach them because we reach all the way to the superlattice Dirac points. We haven't seen much of an effect there. in this type of samples, I have data which I have not shown here, where when we reach the function of singularity, we see also an insulating state at those energies.
So for graphene on graphene, you show us that the tech is basically change the Fermi, but also
Well, yeah, that and more, but
zero energy.
at zero energy, yes.
Thinking about red, also get a certain stacking order, a gapless parabolic phase. Have you,
Yeah, that's Bernal stacked bilayer graphene.
this is not your lab.
No, this is something that we've done, the whole community, a lot of experiments. If you have Bernal stacked bilayer graphene, which is, if you take graphite and instead of taking one layer, you take two, that's what you get, Bernal stacked bilayer graphene, 0 degrees rotation between the two layers. Your energy momentum dispersion is quadratic, it's not parabolic, it's hyperbolic. Okay, and it's not given by the Schrodinger equation, it's by a modification of the Dirac equation. Okay, so you also have a zero energy Landau level actually, with twice the degeneracy, with 8-fold degeneracy. Okay, so it's a complicated Landau spectrum and it's a different equation. It's not Schrodinger, it's not massless Dirac, it's something else, which gives you also zero energy Landau level. And there have been plenty of experiments, my group too, done on this system.
So the Hofstadter butterfly figure, I mean, the original paper, that was for scroll lattice. So presumably that's like
Yeah, for a hexagonal lattice is a little bit, it's a different butterfly, you know. I think we showed this one because it's a bit more beautiful than the hexagonal lattice one, but you know, but it's there is also a fractal, yeah.
Yeah, I believe so, but I'm just curious how deep was that?
It's hard to describe the difference in appearance between two fractals, so I can't do it right now. But yeah, you can just Google the Hofstadter butterfly for a hexagonal lattice and it's for a honeycomb lattice, and it's different. Yeah. Yep.
So as a follow-up question, so are you aware of other systems that people have realized with the Hofstadter butterfly?
So I included a couple of references to systems where people had a 2-deck and they lithographically defined gates to create a periodic structure. Yeah. The problem is that no matter how good your lithography is, turns out that it's worse than, you know, atomic lattices, you know, stacking on top of each other. So the features that they could see, first of all, because the lithography, the length scales were larger, the energy scales associated with the features were smaller, which means that at the temperatures and at the levels of disorder that they had available, the features were not as pronounced as in what we have. So it was, you know, there was evidence of it, some strong indications that people had seen the Hofstadter butterfly, but it was not as pronounced as in these papers.
If I remember correctly, I think you that.
Oh, so yeah, exactly. So more recently, after our experiments, two groups at MIT, Wolfgang Ketterle, and in Germany, Emmanuel Bloch, have realized the Hofstadter Hamiltonian and something, but it, you know, it's, you know, they have the Hamiltonian and so on, but the data and the manifestations are not the ones that we show, right? But they are able to extract the terms and the things, and they have also evidence of the Hofstadter thing in cold atoms, yes. Sorry, yeah, I thought you meant earlier, you know. Yeah, that was on about a year after our experiments, yeah. Yep.
You said something about the varying mass and expecting.
Yes.
But isn't it kind of trivial? Not
No, it's exactly, you know, it's exactly, I mean, Charlie, correct me if I'm wrong, but it's exactly what you would expect, exactly a Jackie Revi soliton, right? When you're inverting from AB to BA, changing the sign of the AB and ABA sublattice symmetry breaking. Provided you prefer, yeah, exactly. So it is that one. You can, you can literally put plus voltage, you know, on the A sublattice, minus voltage on the B sublattice, and then a bit later in space do the opposite, and that is a change sign of the mass term. Yeah. Thank you.
Well, so in the meantime, you should proceed to the 11th floor if you're doing a poster to hang up your poster.
So did you just say that
It's
when
just
you
one floor down.
this is where Van Hove is?
Yes. There. Yeah.
Yeah. So did you just say that it's actually insulating there?